So good morning, everybody. Bom dia a todos. Este é mais um seminário do ciclo de seminários do Observatório Nacional da Coordenação de Astronomia. And today, I'm pleased to introduce you to Dr. Vanessa Hill from Observatoire de la Côte d'Azur in France. So Vanessa did her PhD with Monique Spitz in Meudon, and then had some postdoc positions in São Paulo at the USP with Beatriz Barbuí, and then in ESO-Garching, Paris-Meudon. She finally joined the Observatoire de la Côte d'Azur in 2008. So her work is dedicated to abundances from high resolution spectra in various environments, such as dwarf galaxies, the galactic bulge, first stars. She's a Gaia enthusiast, and she's heavily involved in WEAVE as the PI of the galactic archaeology surveys. She's involved in a number of national and international committees, as for example, she's now the French representative at ESO Science and Technical Committee. So Vanessa, welcome. Thank you very much for accepting our invitation. And Vanessa will talk to you about the pristine Milky Way. Thank you.
Okay, thank you very much for the invitation. Let me start the screen sharing. Ta-da! I don't see my screen yet. Yes, now I do. Can you see my screen properly?
Yes.
And it is moving? Yes, good.
Yes.
Okay, so thank you very much again for the invitation. And what I will try to talk about today a bit is to introduce you to a survey that is called the Pristine survey, and that is trying to look for very metal poor stars in the galaxy as probed of the early galactic evolution. And I will give you a number of the applications that stem off that survey, including also the very large effort that we're making for following up these candidate very metal poor stars with the WEAVE facility. Now I cannot move anymore. How come? Yes, now I can. Okay. So why are we interested in metal poor stars? Well, I mean, the very basic fact is that a star that would be very low mass, for example, a 0.5 or 0.8 solar mass star that would have been born at the very beginning of the universe, say 13.5 or 14 giga-years ago, would still live today as a low mass star on the mate sequence and then evolving to a red giant and so on. And so if low mass stars with absolutely no metals, so with the Big Bang nucleosynthesis composition were formed, then they should still be around in our galaxy and around our galaxy today as probes or fossils of these very early epochs of the evolution of galaxies. And these stars that would be with zero metallicity are commonly called the population 3 stars, and they're believed to be formed something like a few 100 million years after the Big Bang itself, and to be formed really as the very first structures that form together with the first galaxies and systems that will then become galaxies. And the question is, can we really find these first stars or these stars with zero metals? And you will see very shortly that up to now we have not found them. And so what we're looking for is stars that would be as close as possible to that very pristine initial chemical composition, so with the lowest possible content of metals. And in particular, we are focusing on the regime which is called the extremely metal poor star regimes, where stars have less than the thousands of the solar metallicity. And why we're really interested in these things is, of course, that they are the traces of the earliest epochs of the universe. And in particular, they bear special importance to understand how star formation proceeded at these very early epochs, and specifically with no metals. They are also the fossil record of these zero metal first stars, in that the today's properties of the extremely metal poor stars reflect what was produced by the population 3 stars in terms of their chemical composition. And this has very strong impact on understanding the nature of the population 3 stars, and also the first chemical enrichment processes in galaxies. And these enrichment processes have had to be very local at the very beginning, in the sense that very massive stars might have exploded and polluted only a limited environment, and so that the mixing processes in the interstellar medium is also very important to understand how these early chemical enrichments occurred. One of the interesting ideas also for looking for very metal poor stars or extremely metal poor stars is that they might also be or bear the traces of the earliest accretion event onto a galaxy the size of our own galaxy. And so in my talk, I will go through a short introduction on very metal poor stars and where we stand. And I will concentrate then on the Pristine survey, which is a new way of finding very ultra metal poor stars. And we'll give you some examples of what we have found with Pristine candidates in terms of the lowest metallicity stars and their orbits. What we are now finding, or how Pristine is helping understanding stellar streams on our galaxy, and also results in the galactic bulge. And finally, I will finish up by this short description of what the WEAVE facility is and why it is important to follow up very metal poor stars. And before I really dive into it, just a short slide on the naming of things. Since 2005, Tim Beers and Norbert Chrislieb introduced the following notation, where a metal poor star is something that is anything that is with a metallicity below 1/10 of the solar metallicity. Very metal poor stars is metallicities below -2, extremely metal poor stars below -3, ultra metal poor stars below -4, mega metal poor stars down to below -6. And at this point, this is I mean, you could continue with these notations below this, but this is where it stands at the moment, because this is what describes what we have actually found so far. And the first problem is, of course, the following, is that has to do with how stars formed. So star formation with zero metals actually has to have happened with a slightly different condition than what it does today, because the lack of metals also means lack of cooling of the gas into a star. We know since quite a while that this might be okay for high mass stars to form. By high mass, I mean masses above 10 solar masses, or even above 100 solar masses. But what about the formation of low mass stars, which would be the condition for being able to find population 3 stars, low mass population 3 stars in the local universe? Well, despite decades, now 3 decades of searches, we have not really found any metal free star in the Milky Way, and this gives you the metallicity distribution function, either raw on the left here or corrected by biases of or by the selection function of the samples as a function of the metallicity for really the tail, the metal poor tail of our galactic halo. And what you see is that below -4, nothing much is happening. And as a matter of fact, the current record holders are now around iron abundances -7 or so. And so we have not found any metal free star, low mass metal free star, and this might very well be the result of the formation of the first stars. And in particular, if the star formation in zero metals produces only high mass stars, then of course you would not expect to find any today any metal-free star. However, there have been some scenarios put forward, in which low mass stars can form in a very, very low metallicity environment, or even zero metallicity environment, and I cite here a few of them. So, for example, cooling by dust instead of by metal lines, followed by fragmentation, has been shown to lead to the formation of low mass stars, and these stars would then be formed only above a certain critical metallicity Z of the order of -5 or so. Another scenario in which it is not the overall metallicity that really counts, but simply seeing that the fine structure of either carbon or oxygen can lead to efficient cooling, so that the critical or the floor for the lowest metallicity would not be anymore expressed in terms of overall metallicity, but the critical abundances would be that of carbon and oxygen. And again, with a floor with the order of carbon -5 or so. The fragmentation of in the accretion disk can also stars, probably in multiple systems. And in this case, because this is really the fragmentation in the disk around a forming massive star, there would not be any theoretical floor for the lowest metallicities found for low mass stars. And indeed, when one looks at the record holders today of the very, very metal poor stars, the ultra metal poor stars in the galaxy, we currently know something around 10 stars with metallicities, so with iron abundances below -4.5. And 7 of these 10 are either very or extremely carbon rich. 2 have carbon upper limits that are compatible with being carbon rich, and only 1 is carbon normal. And this has lent quite some support to the scenario in which indeed the carbon and the oxygen abundances are the very critical elements for determining whether a low mass star can form or not. And the current record in terms of overall metallicity happens to be that one non-carbon rich or carbon normal star by Elizabeth Caffau a decade ago now here, that would be in the forbidden zone or close to the forbidden zone for both the scenario for the metallicity, low metallicity floor, or low carbon abundance floor for the formation of low mass stars. We also know what the metallicity distribution looks like in dwarf galaxies, and up to now, for the few dwarf galaxies for which we have been able to obtain sufficient numbers of these very metal poor stars, what we see is that it is quite indistinguishable from the metallicity distribution of the galactic halo, which is interesting because it is also telling us that the environment in which these very metal poor low mass stars have not been different in low mass galaxies in which few extremely massive stars may have formed, or in larger halos like the ones of the Milky Way, where you can expect to have many of these extremely massive first stars exploding. And in the last few decades, there has been these searches, very intensive searches for finding metal poor stars, and also in the last 2 decades, very intensive studies of elemental abundances of the very metal poor stars in the galactic halo. And I put just here a few references, but there are many more. And I'm not going to concentrate on that part of the very interesting things that can be done with very metal poor stars, which have to do mostly with characterizing the first stars from their chemical legacy to the next generation of stars. What I'm going to concentrate on instead is giving you this introduction to the Pristine survey and putting it in perspective a little bit. This search for extremely metal poor stars have started in the 80s by looking with the objective prism with very important surveys by Beers, Preston, and Checkman, and then later on with the Hamburg-ISO survey by Chris Lieb at the end of the 90s. And these surveys have concentrated on very strong metal lines in the blue part of the spectra, which are the calcium H and K lines that you see here at very low resolution in an objective prism spectrum from the Hamburg-ISO survey. And this has led to the discovery of essentially more than half, I would say, of the known extremely metal poor stars that we know of today. In the years 2000, another generation of searches have started using the blind spectroscopic surveys. By blind, I mean not trying to pre-select in advance for very metal poor stars that have been provided by the SDSS, Segway, BOSS, eBOSS, etc., but also RAVE, Apogee. And now there will be also the Gaia RVS in this list of large spectroscopic surveys. And those have also come up with quite a large return of metal poor stars. And what is even more new in the game is to start using narrowband photometry to measure the stellar metallicity down to the lowest metallicities. One can measure stellar metallicities with broadband spectroscopy, but at the lowest metallicities, the signature of the metallicity is so weak that it is virtually impossible to disentangle it from other signatures and really derive a precise metallicity. So the narrowband photometry surveys that are currently ongoing are SkyMapper and Pristine. Both use the calcium H and K narrowband filter that is basically using the same region as what the objective prism spectra were using and making a photometric filter on top. The principle is very easy, is to have these filters, and you see here spectrum at high resolution, this time of very metal poor star, very metal poor giant in this case, in the blue with the H and K lines very prominent. And you see on top the shape of the SkyMapper filter in gray and the Pristine filter in red. And the principle is that if you can measure the flux of these in the region that contains very strong metal lines, it will be very sensitive to the metallicity of the star. And indeed, SkyMapper, which has started more than a decade, almost 2 decades ago now, has had a number of problems at the very beginning with the instrumentation and so on, but are now in a very nice production mode. And you can look at the Casagrande paper from 2019 with very nice metallicities. And there's also more recent papers coming out, including by Shitty this year, showing different ways of measuring the metallicity in the SkyMapper photometry. And what I'm going to talk to you here about is the Pristine CFHT photometric survey in this narrowband filter that has been led by Else Starkenburg and Nicolas Martin for the last few years. And I will show you where the survey is and how it functions and what we can do with it. So this is a map of currently what the Pristine coverage is. This time it's in galactic coordinates, and the underlying image you see here is Gaia. And in blue on top, you have all the area that has been covered with the Pristine narrowband filter. The idea of that is in fact to obtain only the narrowband filter with the Megacam camera on CFHT, and to combine it with other sources of broadband filters to measure the metallicity. And in particular, one of our prime surveys to which we compare the narrowband filter photometry is the SDSS. And this is now showing you Pristine in orange on top of the full SDSS coverage. And we are currently at something like 35% of the SDSS coverage. In fact, Pristine is functioning as a bad weather program on CFHT. And so it is progressing very, very nicely in terms of the number of square degrees that we are getting per year. And this has allowed us to actually be much more to be more ambitious than what we started off with. We started off aiming at 3,000 square degrees and then 5,000 square degrees, and now we are already close to 6,000, and we really have now the ambition to cover all of the northern celestial hemisphere with that broadband filter. So how does it function? These are now giving you the Pristine filter on top of different synthetic spectra computed for different models, from the cooler models to the hotter models, and each of the different colors are different metallicity, ranging from solar metallicity in red to -3, so extremely metal poor stars in blue, and without any metals in black, showing you what it would look like if there was no calcium in the star, no calcium and no other metals in the star. And what you see here is a passion line. The only line that is there in black is the hydrogen passion line. Not passion, sorry, Palma line. So the way this calibration works is that we are comparing the photometry in the narrowband filter with broadband colors in color space, which we have manipulated a little bit with a color term here as well, to make it look nice and flat with different metallicities. So each the color code for the points here are the metallicities, the observed metallicities, spectroscopic metallicities from SDSS Segway stars. And the lines show you where the calibration lies. And you see that in this space, the metallicity of the stars separate out very nicely. And in particular, it separates very nicely between stars that are very metal poor and extremely metal poor and beyond, which is what we were really looking for, is the accuracy of the metallicities at the lowest metallicity range. And on the right-hand side here, you see the comparison of the Pristine metallicities with the spectroscopic metallicities. And this is a bit of a circular argument, because these are used to make the calibration, the spectroscopic to make the calibration. This is what we retrieve from the model. And this, as a comparison, is using the broadband colors only metallicity calibration by Ivesic in 2008. And you see that although at high metallicities things are going pretty nicely, at low metallicities the broadband photometric calibration goes berserk and is not sensitive to metallicity anymore. This is now the same plot, but updating you with the current calibration that we have. So lately, we have been adding different kind of sources of spectroscopic metallicities to help with the calibration of the Pristine space. So adding to SDSS Segway also Lamost metallicities, and also our own follow-up of Pristine candidates that have been published in these two papers by Chris Joachim and David Aguado in the past years. And one of the other improvements that we have made is that although this space is meant to separate on the x-axis the effect of temperature on the spectra, and on the y-axis the effect of metallicity in the stellar spectra, also gravity plays a role in the location of a given stellar model or star in this space. And so we have refined the calibration now, separating for dwarfs on the one hand and giants on the other hand, and it is helping reducing the dispersion of the metallicities that we obtain for the photometric metallicities. What we have measured at this point with the follow-up that we have is that our efficiency at selecting stars below -2.5 of metallicity is close to 70%. While selecting stars below -3 of metallicity is close to 22%. This is, in fact, might seem to you like low numbers, 22%, but it's actually something like an order of magnitude better than any other survey had achieved before Pristine. And indeed, I mean, from the first follow-up, we found already Pristine 221, which is a star of metallicity -4.6 in 2018. So let me now walk you through a few of the applications that I found extremely interesting and that I'm involved in specifically from the Pristine survey. The first of them is to look specifically at what we see in the anticentre, combining Pristine and Gaia. What is particular at the anticentre of the Milky Way is that because the longitude is 0 and I wrote it wrong, of course, the longitude is 180 and the latitude is 0. Then we have that the rotational velocity around the galaxy is equal to the velocity in longitude, which is the product of the distance of the star and its proper motion in the L direction. This is really a nice property, and it is conserved to something like better than 10 kilometers per second, as long as we stay in this box here depicted in orange, which is basically around L of 80 and below B of 40 in absolute value. And the very nice property of this is that it means that if we have the Pristine photometric metallicities, and from Gaia we get the distance from the parallax and the proper motion, then we can investigate how the stellar populations towards the anticentre direction rotate as a function of metallicity. And this is a very powerful tool to disentangle what kind of populations are present in that sample. So this is what we are doing currently with Emma Fernandez Alvar, who is a postdoc in Nice with us. And we are submitting a paper next week on this subject. And you see here the main plot of the paper, which shows you this VL, which is a surrogate of the rotational velocity around the galaxy as a function of the metallicity, and the metallicity is the Pristine photometric metallicity towards the anticentre. What you see is that, as one would expect when you look essentially through the disk towards the anticentre, you are dominated by a disk-like population that is rotating. With the reference system that we are using, left-handed reference system, the sun is rotating at minus 220 here. So the thin disk would be something around these rotational velocities. And indeed, what we see is that most of our sample is in this region, which is fast rotating stars, rather metal-rich stars, and this is really because we're looking through the disk. So the thin disk is at least something like 60 to 70% of that sample. What we also see is a rather prominent thick disk that is here with slightly lagging behind the thin disk, so with not rotating as fast as the thick disk, with slightly lower metallicities, and we have done this. This is not the best plot to look at it, but we also see that the rotational velocity of the thick disk decreases with the metallicity decreasing within the thick disk. And what we also see is this prototypical halo that is non-rotating or slowly rotating, and that we detect down to the lowest metallicities. These are the things we were expecting to find, and we did find. More surprising is that we found that this rotating population, fast rotating, rotating as fast as the sun, essentially, exists not only at high metallicities, but down to at least -2.2, and with a tail extending all the way to the extremely metal poor stars to -3.5 or so. This was, of course, quite a significant surprise, and I will return to it in the next slides. Other properties that we found is that we also find very clearly the trace of what is called a splash, which is basically the thick disk that has been heated by the last large interaction with the Milky Way that we know today, that we call today the Gaia Enceladus satellite merging, or the Gaia sausage, depending on who you talk to. So it's now becoming more and more usual to call it the Gaia sausage, the Gaia Enceladus sausage, to mix both vocabulary for the same thing. And the interesting thing about the trace of this splash is that if you concentrate on the contour here, you see that it is at the same rotational velocities. You do see a continuation of that splash all the way to metallicity -2. And one of the last things that we saw is that the metal poor halo seems to be slightly retrograde. So looking again at the metal poor part of that diagram, and looking more precisely at the distribution of the rotational velocities, you see that in the metallicity regime between -1.5 and -2, there is clearly two big populations. One that is with a rotational velocity slightly retrograde, and that we associate to the halo. And then we have this additional population that is rotating as one would expect of a thin disk. We detect this very robustly down to -2, statistically very robust. However, when you go to the metal poor tail, so between -2 and -4 here, you see that this population still exists. It is this small little peak here that is not statistically significant to a very high level. But however, whatever is used as a Gaussian mixing model to fit the global distribution, it always appears as a small excess, and we really believe it is the tail of that population. This is not the only property of this metal poor thin disk or high rotating stars to very low metallicities. When one looks at the anticentre, the vertical velocity also it can be measured relatively simply as a function of the proper motion in the B direction this time. This is what we have done here, is to show you the same plot where you have rotational velocity as a function of metallicity, but this time we color code this space with the vertical velocity. And what you see is that this tail of metal poor stars that are rotating very fast, they also have very small vertical velocities. showing that these stars are in fact confined to the plane of the Milky Way. Not only are they rotating fast, but they're also confined to the plane of the Milky Way. And this is also backed up by the fact that we only find them at relatively low heights above the plane, and not at the highest. When we are above 2 or 3 kiloparsecs above the plane, this population has completely disappeared. So the origin of this population, we were wondering ourselves, of course, and this is very much in line with other results that came from Sestito in 2019 and 2020, and Paola Di Matteo last year, that seemed to find traces of these rotating planar extremely metal-poor stars or ultra-metal-poor stars. And here is an extract of the paper of Sestito in 2019, where he shows here this is in action space this time, but basically it's again showing you the rotational velocity and the vertical velocity of all of the known ultra-metal-poor stars, so stars with metallicities below -4, and you see, as expected, a population that is rather kinematically hot, that is the main halo, and you see this population of planar rotating objects here, with a strong number of them being prograde. So they're not all prograde at the velocity of the sun, but they are significantly skewed towards prograde. And this is just an example of one of those planar orbits that are found in this sample. Up to 25 to 30% of these ultra-metal-poor stars are in these planar orbits, meaning that they reach at maximum 3 kiloparsecs above or below the plane. Paola Di Matteo was also showing that this population at the very lowest metallicities, in fact, occupies similar locations in the Trumre diagram, where you have the rotational velocity here and the velocities perpendicular to the rotation here, as more metal-rich stars. So if we start from the more metal-rich stars of apogee here, you recognize here the thin disk, that is the densest region appearing here in pink, the asymmetry here in orange, which is the thick disk, and the halo stars were expected to lie basically anywhere here, but you see that even at the very lowest metallicities, you do have stars that lie where the disk would expect to be. And so this parenthood of the ultra-metal-poor, the extremely metal-poor, the very metal-poor stars with populations at higher metallicity is prompting this idea that perhaps there was a gaseous disk present in the very, very early Milky Way, before the first giga-year of the Milky Way, and forming stars in this gas. So it needed to be cool enough to form stars at that time. And what we see as these rotating extremely metal-poor stars will be the remaining of this population. And this is very, very interesting, of course, in the context of the formation scenarios for the Milky Way. Another thread that I wanted to give is the very metal-poor stars in the bulge. According to the Lambda CDM simulations, we expect that a sizable fraction of the first stars or the most metal-poor stars should have fallen into the central parts of the Milky Way, which we know today as the bulge. This is some endeavor that is very hard, because the bulge is made of very many very metal-rich stars, so that the extremely metal-poor stars will be the needles in a very, very, very big haystack. The only survey that has really had the ambition to search for EMP in the bulge before Pristine was EMBLA, which is the Sky Mapper version of Pristine. And what we call PIGS, which is the Pristine Inner Galaxy Survey, is doing exactly this with the Pristine filter. And these are the fields that we have now obtained around the galactic bulge. and the color space in which we select for metal poor stars is exactly similar to the one that we do for the halo. The only difficulty here is that the location of stars in this diagram are impacted by errors on the reddening, because you see that this diagram is of course made in unreddened colors. And so extinction is complicating the picture a lot. This is why we are staying away from the highest extinction regions of the bulge. The other peculiarity is that because we're looking to the bulge where the main population is 8 kiloparsecs away, we are concentrating on giants rather than having a mix of everything as for the halo. Of this survey, we have been able to measure of the PIG survey, we have been able to measure the metallicity and confirm the metallicity from a follow-up of spectroscopic follow-up using the AAO omega. We have now a sample of almost 2,000 very metal poor stars, so stars below -2 in the galactic bulge. And what we have seen is basically, I'm showing you two main results that come from that survey. So you see the metallicity distribution for our metal poor stars in the bulge, which is really very much tilted towards metal poor, which is what we wanted. And so the first result is that we were able, from the spectroscopic follow-up, to measure also the carbon. And as I was explaining at the very beginning of the talk, carbon is a very interesting element to understand extremely metal poor stars, because they do contain a lot of carbon-rich stars. And what we are seeing here, comparing in black here the points in the galactic bulge to the colored points which are in the galactic halo, is that we are missing a lot of the metal poor carbon-rich stars in the bulge. In fact, this is mostly at the higher metallicities, in the sense in this boxy part of the diagram that we are missing most stars. This is statistically very significant, the difference. One of the possibilities would be that the way we select stars with the photometric metallicities might be impacted by the carbon content of the stars, in the sense that in the calcium H and K region, there is also CN bands that can enter, and that could potentially avoid us from selecting some of the carbon-rich metal poor stars. But exploring these biases, they do not seem to be large enough to reflect the difference that we are seeing in the fraction of metal poor carbon stars that we are missing in the bulge. And so we are suggesting that this might be rather a true property that could be expected if the building blocks that fell into the galactic bulge had a very quick enrichment history that would then go against the most metal poor carbon stars. The other result that I wanted to highlight, thanks to this very large sample of very metal poor stars in the bulge, we were able to look at the kinematics of metal poor stars, and to link it to the kinematics of at higher metallicities. So at higher metallicities in the galactic bulge, one sees this very nice cylindrical rotation. This here is the mean metallicity, the mean rotational velocity as a function of the longitude in the galactic bulge, and this is this is the literature results here, and these are in colored the stars from from Pristine, from the pigs survey. And while we recover very nicely the kinematics at high metallicity, what we could do for the first time that no other survey could have done before is to look how things are going at low metallicities. And what one sees is that basically the bulge is rotating less and less as you go to lower and low metallicities. And at the same time, the population here now is the velocity dispersion. And the velocity dispersion here is going higher and higher as the metallicity decreases. And so this is very much in line with a hotter, kinematically hotter population that the origin is still under debate a little bit, whether this is really a spheroidal component linked to the early accretions that ended up in the galactic bulge, or whether this is the inner part of a thick disk or extremely metal poor disk that is still coexisting with the younger bar inside the Milky Way, in the very inner parts of the Milky Way. The last applications that I wanted to tell you about is Pristine with stellar streams. As you know, very many stellar streams were discovered by Gaia, essentially in the galactic halo, using proper motions, phase space, and so on, very recently. And here I'm just showing you one of these very large efforts that was led by Rodrigo Ibata in the last years, using the stream finder algorithm. That is using basically any single information between the astrometry of the stars, so their proper motions and distances, but also the colors and the magnitudes of the stars. And it is basically finding the best large circle that would be around the galaxy and measures how many stars belong to a given large circle and attributes a certain probability of being part of a stream based on these aspects. And so what you see here is the different streams that were published from the Gaia DR2. You see there are very many. This algorithm is really designed to look for kinematically cold and spatially coherent streams on the sky. Here, the color coding is the proper motion in B. What we can do with the pristine metallicities is to look at these streams again and actually measure the metallicity of the stars that have high probabilities of belonging to one of these structures. And so this is what we have done. This is a paper by Nicolas Martin that has been submitted in December, last December, and is now out. And this shows you up on the upper plot all the stars that are in the stream finder solutions and color coding them by the metallicity. And below you see the same stars, but this time color coded just by the stream to which stream finder attributes them. And the great interest here is that we can, first of all, confirm whether a stream is really a stream, in the sense that it has some coherence metallicity-wise, and also characterize what kind of progenitor it comes from, based on the metallicities of the stream and also on the metallicity dispersion that we find in the stream. And there are some very nice examples here. For example, you see here a stream that appears to be extremely metal poor, below -3, that I will talk to you about in 1 second. And while some other streams here were crossing, and thanks to the metallicity, it's clear which belongs to which stream. So here you see that the Fjorm stream is much more metal poor than the M5 stream, which is this arc here. So there's really a huge potential in using these large-scale metallicity maps, photometric maps, to help understanding the streams around the Milky Way. And just to give you a glimpse of this very interesting stream that we found that appeared to be extremely metal poor based on the pristine metallicities, we have obtained also now spectroscopic metallicities to confirm this. And this is the HR diagram of the stars that are falling along the stream path of Stream Finder. The large things are the spectroscopically measured stars, and the small symbols are the pristine metallicities. And you see that although pristine has quite some dispersion on the metallicity measurement, and this is the PDF here that you see, the metallicity distribution. Every single everything agrees to say that this stream is extremely metal poor. In fact, the mean metallicity is minus 3.3. The dispersion around this mean metallicity is compatible purely with the distribution of errors. So there is no native metallicity distribution in this dispersion in this system. And furthermore, from the spectroscopy, we could find a dispersion in or anomalies in the sodium abundances in some of the members. And so we are convinced that the progenitor is a globular cluster. And this would be by far the most metal poor known globular cluster, both around the Milky Way and any other galaxy that we have ever found. This is, of course, a dissolved globular cluster, but still tells us something really important on how a population of really strong, very metal poor globular cluster must have existed and might have dissolved in the Milky Way. The last things I wanted to touch on, and I see that I'm already short in time, so I will try to be quick on this, is to tell you a little bit about the wide field multi-object spectroscopy spectrograph in the north that is called WEAVE. This is a project that is led by all these institutes. The PI is Gavin Dalton in Oxford, and the project scientist is Scott Traeger in the Netherlands in the Captain Institute. WEAVE is a facility that is being currently integrated into the 4-meter telescope, William Herschel telescope in La Palma. These are all the participating countries. In a nutshell, WEAVE has two different spectroscopic modes, high resolution around 20,000 and a low resolution around 5,000. The coverage of the low resolution mode is continuous between basically 37 angstrom all the way to close to 1 micron. While the high resolution has 2 windows that you can choose out of 3 possible setups. And it has on the sky 3 possibilities. It has a large IFU that is quite large on the sky, that is depicted here. It has the possibility of having 20 small IFUs, which are 2 by 3 arc seconds on the sky. And it has a MOS or Medusa mode, where you can allocate each of 1,000 fibers individually wherever you want in the field of view, which is 2 degrees in diameter. I'm not going to describe you the spectrograph or anything like this, except to tell you that the way the spectrograph was designed was really with in mind very strongly the complement to Gaia in 2 different ways, to get radio velocities where the Gaia onboard spectrograph cannot, because stars are too faint. So basically for stars fainter than 15 or 16th magnitude, and all the way down to the Gaia limiting magnitudes for the astrometry. And it has a high resolution mode, which has been defined to be able to obtain a detailed chemistry for stars that in Gaia will not get any decent chemistry from the onboard instruments. And with stellar parameters in either of these two modes, the idea is to be able to enlarge the volume in which the Gaia transverse motions, so the proper motions, can be usefully turned into velocities by measuring spectroscopic distances. The WEAVE Galactic Archaeology Surveys, for which I'm the PI, at a glance looks like something like this. This is a Gaia density of stars background image in the northern hemisphere. So the shape here is basically a declination limit of -10. Which is where La Palma can usefully observe. And the different galactic archaeology surveys are here depicted in different colors. And the ones that are important from the point of view of WEAVE are the big yellow contours here, which are the high latitude, low resolution survey, and the black dots here, which is the high resolution survey. And in both of them, we have an agreement with WEAVE to observe very metal poor star candidates from Pristine on top of the normal target selection function for the surveys. And the result is that we expect, once we take into account the overlap between here's the HR survey in blue and the Pristine coverage in black, or here the low resolution WEAVE survey with the contrary, here was the low resolution, here is the high resolution WEAVE surveys with the Pristine background. Once we take all of this into account, we expect to have low resolution spectra, so low resolution being 5,000 resolution spectra, so perfect to measure both metallicity, but also a number of the key elements in these spectra. For 40,000 extremely metal poor Pristine candidates, and something like 10,000 at high resolution, which we will select with a more generous upper limit for the metallicity of -1.5. And so all of this together shows you that this is going to be a huge leap in our understanding and using very metal poor stars and extremely metal poor stars to understand the early Milky Way. Thanks to this combination of the Pristine survey together with WEAVE. And with this bright future, I think I should stop because I'm already over time quite significantly.
Thank you very much, Vanessa. It was really a nice talk. And we have some questions here. Marcelo, can you start, please?
Hello, Vanessa. Thank you very much for this very nice talk. Can you see me?
Yes.
Oh, okay, great. So thank you very much for this very nice talk. It was very, very interesting. I have just two very general questions for you. The first one is, could you talk a little bit more about why Z = 0 is okay for high mass star formation?
I mean, basically, it's just a matter of the equilibrium between how much mass you have to collapse, and how much of the energy is available to be radiated out. And so basically, it has to do simply with the gene's mass.
Okay.
The gene's mass depends on what you have as coolants.
Okay. And the other question is considering the Pristine survey. So you have just a narrow band filter, okay, around the calcium-2 lines, correct? So how is the interstellar contribution taken into account, or is it simply negligible since you are pointing to halo stars and not and avoiding the bulge stars?
Yes, so we are taking it into account because it is important everywhere. Of course, in the halo part of the survey, it is less important, but it still needs to be taken into account. And we are using basically, depending on what is the exact application, we are using usually the integrated maps of the interstellar extinction, or for more local applications, we are also using 3D extinction maps to take into account the distance of the star. And then this is for the extinction, and then to turn it into color excesses, we are using essentially a combination of reddening laws, and for the Pristine filter, we computed, of course, the conversion of the total absorption to the Pristine filter. And this is quite a significant contribution of the total uncertainties that we have on the metallicities. In the galactic bulge, for sure, is the dominant one. And then it is not negligible when we are also trying to use the Gaia colors to make the calibration for the brighter stars that are saturated in the SDSS or PanSTARRS or other surveys like this. And because of the Gaia bands are so wide, it is also critical there.
Okay, thank you, Vanessa.
Welcome.
Thank you. So Carlos Andres also has questions.
Yes, just open my cam. Can you hear me? Yes, okay, perfect. So thanks for this nice talk, Vanessa. For me, it was very useful, very great, because I'm working on my PhD project in that topic as well. So I just have two questions related with Pristine. So in the first part of your talk, you explained that, well, you use Pristine to calculate the metallicities, taking the advantage of the narrow band filter, and you say that there was a percentage of 70% success of 70% of choosing very metal poor stars, and 22% of selecting extremely metal poor stars. But so, well, that percentage, that success rate was calculated in the way that you choose those stars, and then you follow up spectroscopically some of the stars, and, well, how those values were calculated. And then, well, my other question related is when you at the end of your talk, when you were explaining the stellar streams calculated with using Gaia, you said that, well, there was a work that was published using the metallicity calculated from Pristine to those stellar streams, and I saw that there was some values below than -3 or even, I think, -4. So how reliable are those values in that limit of -3.5 or -4? Thank you.
Yeah, both interesting questions. Okay, let me go back to this slide that tells you, so the percentage is measured, is really a success rate, in the sense that we selected stars that were that had spectroscopic metallicities from Pristine, and we did a lot of follow-up, not only of the most metal poor, but of everything. And no, I mean, not everything, but with various degrees of predicted photometric metallicities. And so out of the stars that Pristine was predicting to be below -2.5 of metallicity, 70% of them were spectroscopically. But of the stars that Pristine were predicting to be below -3, there were 22% that really were. However, the 78% remaining are also metal poor stars. It's just that they are not below -3. So it is not telling you, because this we don't have yet the means to do it very nicely, except in globular clusters, but this stops at -2.5. But it's not telling you how many stars, if there were 100 stars at -3, how many would Pristine recover, which is the other way of looking at things. And for this, it is very hard for us to do it properly, because as I say, for the moment, the only good samples we have to do this is our globular clusters, and they are both not so metal poor, and also they are crowded area in which the photometry has a lot of issues independent of what we see in the field. Then your second question was about the streams. So let me go back to the. It's this thing you mean, right? So just to clarify, on the bottom part of this, the streams are color coded just by the stream. So for example, M5 might be black. It doesn't mean it's -4. It is black because it is the color for M5. Okay. So I'm not sure what your question was. So you said that on this map here, there are some candidates very metal poor, and that you're not sure how reliable the metallicities are. I guess this is the question, right?
Yes, especially in that part below -3, because
yes.
You say that Pristine has the ability to calculate accurately the metallicity up to -3.
Yes, so there is no floor in which Pristine does badly the metallicities. But there is a different sensitivity also because of the shape of the calibration or the color plot. For hotter stars, the error will be larger than for cooler stars, and for more metal poor stars, the error will be larger than for more metal rich stars. I think some answers to your question are shown here, in the sense that we believe that all of the stars here that are yellow, or well, basically that all the stars that are here are probably stream members. And you see that among the ones that are high up, that are cool, the Pristine metallicities are fine, really fine. Among the ones that are hotter, there is more of a dispersion. You have things up from -2.6 to -4 in the predicted metallicities. And there, if we could have spectroscopy, I could bet that most of them will turn out to be where the mean metallicity is, which is -3.5. So it tells you that indeed the error bar for these hotter stars are of the order of probably 0.5.
Okay, thank you very much. I just have one quick general question. Is there a part of Pristine survey that maybe has been made public? I mean, for maybe for have some comparisons with other data or something like that? Because as far as I understood, I was following the Pristine researches, but I couldn't find that the data produced by Stream has been public, or for at least some part of the data has been made public yet.
So what is public is the metallicities, that the photometric metallicities that we have used for the follow-up samples. And so this includes something like, I don't know how many thousands of stars in the Bulge, and it includes close to 1,000 stars in the halo. What is not published yet, indeed, is the full catalog of the sky that we have, and this is something that we want to keep non-public until we start observing.
It makes sense.
Okay, so Vanessa, Renato had to leave for another meeting, but he left 2 questions for you. So I'll read it. I'll read the questions, and then he'll watch your answers in the YouTube later, for sure. So first question, at what Z do models predict that zero metallicity stars would be? This question is motivated by a recently accepted proposal to JWST to look at Z approximately 6 star that has been gravitationally magnified by a factor of 9,000 by a galaxy cluster.
I would not be able to tell you a Z range from the top of my head, but I'm pretty sure that at Z of 6 and beyond, there should be some metal-free stars. However, I mean, it is also clear that at these very early times, chemical enrichment must have happened in pockets and not in a completely homogeneous way. So that I would not be surprised that even at Z of 6 or even at Z of 10, there could be stars of zero metallicities cohabiting with, at other locations, stars with already higher metallicities.
So second question is, since the first supernovae were of the core collapse type, which produce much less iron than type, which produce much less iron than type 1a, which supposedly appear very later on, would it be expected to find stars with no iron, but with other alpha elements? If so, at which Z are they predicted to be?
I'm not sure I understand the question. I suppose this has to do with the fact that that alphas and iron are not co-produced in the same proportion in type 1As and in type 2s or in core collapse. However, core collapse supernovae do produce quite a bit of iron. It's not because they produce even more alpha that they don't produce iron. They do produce quite a bit of iron. And in fact, what we observe in the extremely metal-poor stars, even down to the -4 regime, is that the ratio of alpha over iron is extremely stable. So there's little dispersion. Which tell us, this is something that I didn't go into at all, but it is a whole line of research of understanding really exactly what kind of mixture of supernova you need to make the chemical composition of the extremely metal-poor stars. But it's quite clear that it is at -3.5, -4, it is still not a single shot supernova that we are looking at with a given mass. It is already something that is sufficiently well polluted by a fraction of the IMF, let's say, or a sample of the IMF, so that the alpha over iron ratio is incredibly well defined. There are a few exceptions, but it is really quite well defined, much more than we were expecting a decade ago.
Fernando also has a question.
Hello, Vanessa. Very nice talks. Thank you very much. I want to ask you if you have found any hypervelocity star among Pristine.
So the answer is no, but the answer is also we haven't looked specifically for EMP high velocity stars so far.
Okay. Okay.
What we have done systematically is stars for which we had spectroscopic follow-up. We looked at the orbits, and among those there is no high velocity hyper velocity star. Okay. However, this is a tiny fraction of the Pristine sample. So it is something that could be conceivably done to look, for example, to look at the metallicity distribution of known hypervelocity stars from Pristine. Mm-hmm. We haven't done that. It's a good idea.
Mm-hmm. Okay, thank you.
Okay, I also have a last question. Sorry, Vanessa. So I'm not very familiar with the infrared. But is it possible to define a narrowband filter, such as this filter that we use in Pristine, in the infrared to study the bulge, for example? to detect metallicity?
So another very good question. In fact, there are people who have started looking into making a narrowband filter, not so much in the far infrared, where there are few very strong metal lines, but the calcium triplet in the around the 8,600 angstroms is a very good candidate, because it's triplet that has a very high, that is quite strong. It's among the last to disappear for very metal PanSTARRS. And if you would want to use it in, for example, in the galactic bulge, you would be also looking essentially at cool stars, where you have more of an absorption there. So it is a very good point. To my knowledge, it has not been tried in the galactic bulge, but it has been tried in the magellanic clouds. And it's still a bit early to say whether it is really efficient or not to retrieve metal PanSTARRS.
Okay. So thank you very much. Thank you for your very nice talk, and to share with us your these results with Pristine and the expectations with WIV. We are all anxious about it. So bye-bye.
Thanks a lot. Thanks a lot. Bye-bye.
Bye-bye. Thank you.